Hello, everyone, and welcome back to our plasma physics lectures. This is lecture 14. I don't know why I always have to say that since the number is there, but anyway, that's today's lecture, and we are going to completely change topic. We're going to switch to inertial confinement fusion, or ICF. And the reason why we're doing this is that there have been some recent exciting results from NIF. And I think that's going to be interesting for everyone to learn a little about how ICF works and what is so exciting about the NIF results. We will get to those results by the end of this mini section or section in our course. We're going to only scratch the surface of all that's involved in ICF. And therefore, there is going to be a good amount of hand waving, which you cannot see because I'm not going to have a camera on my hands waving. But we will not go into detail in formulations and derivations and expressions. You may still be surprised by the end of this section, but ICF is actually a field where big simulations are very important, and theory is also quite important, as it is in magnetic confinement fusion. But the fact that Auburn is not involved in ICF doesn't take anything away from its importance and its depth as a field of plasma physics. I do not want to leave you hanging, and you may already be aware of that, but I mentioned a couple of times NIF. That's the National Ignition Facility that is located in Livermore, Lawrence Livermore National Lab. And it's, as of today, the most powerful laser system in the world. Well, at least the most powerful laser system used for ICF, but I don't know of anything else where big lasers are used for lasers of comparable power to what is used, or energies rather, to what is used in ICF. I will probably manage to say a little about the NIF later on, but for now we're going to leave it this and try to start getting into some of the science. The first step in my description of inertial confinement fusion is actually something that is common to any field of plasma physics that is involved with fusion. That's what's called the Lawson criterion. This is again for both inertial and magnetic confinement, or in fact any other configuration that you may come up with, or that people or research groups have come up with in recent years. But this is something we've already mentioned in class, but I will write it down again for you. Here's what it looks like. Well, or rather, here's where it comes from. I will get to what it looks like in a moment. We have 3/2 of n, and that's density. Time derivative of the temperature is going to be equal to E alpha over 16 times P squared. P is the pressure, average sigma V over T squared. T is the temperature. I'll tell you what sigma V is in a second, plus S. I'll put in an H for reasons I will explain, minus C sub B over 4. I don't know why it's over 4. No, I do know why it's over 4. I will tell you. P squared over T to the 3/2 and minus 3/2 of P over tau E. It may feel like this requires a lecture by itself, and maybe it does. I will give you the reference, but all that this is energy balance. In a somewhat special, specific case, let me put this here. It fits great. That is, I'm here assuming that I'm using deuterium and tritium for my fusion reaction. Now, I will not tell you what fusion is and how you can make two small nuclei fuse into a bigger one. You know all those things, and you know that the reaction, the fusion reaction between deuterium and tritium is the most promising one. And that's what I'm assuming. The product of that reaction is actually two particles, a neutron and an alpha particle. That's a helium-4 nucleus. And what I have, the first term on the right-hand side, is the fusion production, assuming that that is the only product, fusion product, that remains in the plasma. So this is fusion power. Let's start putting some arrows, as we always do. Why that's the correct expression? Don't worry about it. That's the correct expression. Or well, I encourage you to read more about it. But all you have to remember that is the fusion power. This is any heating source we may have in the system. Here, not there, here. Okay, heating. Then we have the next term is Bremsstrahlung radiation. Let me spell Bremsstrahlung. I'm sorry about that. Okay, such an easy word. So that's the third term, which I can make it fit there. So I'll put it down here. And the last one is energy losses by conduction, essentially, where I can give myself a little bit more space here for my arrow. And wow, that was unfortunate. Let's try again. Okay, this TAUI didn't do much better this time. Is what is called the energy confinement time. And on the left-hand side, I just have the time variation of the internal energy of the system. I'm assuming that the density does not depend on time. So all that is changing if there is an imbalance between sources and losses is the temperature of the system, where by system, I mean the plasma, and there is a single temperature that is ions and electrons. All ions, all electrons, they also have the same temperature. If you're curious about what happens in the case they don't, please read the paper we wrote in 2017 and the other paper in 2019 about that exact topic. Now, this is typically solved or expressed at steady state. That's the magnetic confinement principle or approach. And in fact, even though things are a lot more dynamic, and there is no such thing as a steady state in ICF, we're still going to use the steady state expression for the energy balance. Really what you do is take this equation. I think I should square it. It's kind of an important. Well, that's actually not the Lawson criterion, but this is the energy balance. Not quite what I intended. So let's try again. Okay. And let me emphasize that this is energy balance. Okay, now what we do is take this equation and assume steady state, or if you prefer, we can only consider the right-hand side. That means we are saying, well, I want my system to be a steady state. What do I need? That's sort of the Lawson original approach. Or I can say, well, what expression do I need in order to have a net increase in energy balance? So to have a positive sign for my derivative of the temperature. And then what you do is to rearrange the terms, which can be done in different ways. But I will just give you a couple of expression, hopefully ideas of how this thing works. But before I do that, I realize I've not quite defined what sigma v is. That's the cross-section for fusion reactions. And it's got that average symbol or those average brackets to emphasize that it's an expression that's averaged over the distribution function of the reagents of the deuterium and tritium that are going to do the fusion reaction, because the microscopic cross-section depends on the relative velocities of the two particles. And of course, we have particles with a lot of different velocities, as is described by the distribution function. And even assuming that the two species have the same distribution function, the same temperature, you still need to take an average over the distribution function to figure out a single number to put in this expression. Okay, now the Lawson criterion, as it's usually written, looks, let me get the correct pen, looks something like this. 2 times n times t times tau e must be greater than or equal to t squared divided by E alpha over 24 times sigma v minus CB over 6 times t to the 1/2. Well, the point is here that the function on the right-hand side is only a function of temperature. That is, once I know the temperature of the plasma, I can tell, well, then the product between the density, the temperature, and the energy confinement time must be larger than a certain number. You may wonder, why do I have temperature on the left and right? It's just the way it's usually written. You could write it without temperature, and indeed, that is the way Lawson originally wrote it. It's product between n and tau. At any rate, that this product and the function on the right is going to be, as I said, a function of temperature, and that's going to have a minimum. It's not obvious, but I promise it's going to have a minimum, and that minimum is at a certain temperature. So that's sort of where you want to operate. You may have heard in some talks or read somewhere that there is this magic number, that's the Lawson number for the condition for ignition, and that's some, whatever it is in whatever units. It's actually, if you use meters to the -3 times kV times 1/seconds, sorry, times seconds, that's tau e, you get a number like 60 to the 10 to the 20, something like that. But whatever it is, the point I want to bring to your attention is that that number is going to be a function of temperature. So be skeptical when somebody shows experimental results or whatever, and they show what we have this temperature of 1 kV in the center of the plasma, but the density is whatever, it's very high, and the confinement time is this high, so we get this number to be, I don't know, 30. So we're almost 50, we're 50% of the way to the Lawson, satisfying the Lawson criterion. And there are two huge problems with that. One, this is a global energy balance. You're not allowed to use the temperature in the center of the plasma to make your numbers look better. You actually have to use the average temperature of the plasma. This assumes that the temperature of the plasma is the same everywhere. So be very wary of any result that uses the temperature and the density in the center of the plasma. Those cannot be used for the Lawson criterion. Other problem, well, if your temperature is 1 kV, the Lawson criterion says that that product should be infinite. You just can't ignite at 1 kV. And that is that you're not 50% of the way there. There is no point, no way to get there. Again, this is all general information, not just for ICF, but these are important things to know. Now, whatever the temperature is, there is going to be, again, some specific number that our triple product needs to exceed. And our task is to make the conditions in the plasma such that that product is satisfied. Sorry about that. Wow. Okay, what we do in magnetic confinement is to take n of the order of 10 to the 20. I'll fix that in a moment. No, by the way. And this is a SI meters to the minus 3. T of order of 10 kV, and tau, but I should just write it. Oh, it's tau also be order 1 second. The 1 second is not going to cut it. You're going to need maybe 5 seconds or something like that. Density is probably going to be a little higher if you can do it, but you're going to aim for the minimum. And again, you have to be careful because the energy confinement time is a global parameter. It's for the whole plasma. So you can't just say, I'm going to satisfy that in the center of my plasma. You have to be a lot more careful on that. The ICF approach is quite different. And it's different in the sense that the numbers are going to be quite a bit different. Okay, let me bring this up a little bit. Now, let's look at the this data, or the numbers that are used in this approach, and since the Lawson criterion function as a function of temperature, as I said, as a minimum around 10, well, 14 maybe kV, that's sort of where you want to be anyway. But densities are going to be quite different. The densities in the inertial confinement case are going to be, ready for the crazy number, about 12 orders of magnitude larger than the value. What happened? Where it go? Sorry, I wrote something that disappeared. Okay, I've never seen that before. Well, there is always some surprise. Let's see. Let me pause this for a moment and try to figure out what my computer is doing, why it's not writing numbers. So sorry about that. Okay, I fixed it. I'm never going to tell you how I did it. Temperature, well, it's going to be about the same. I'm just going to copy from here. Tau E, well, you can see from our expressions above, that's going to be a lot shorter. In fact, it's going to be of the order of a very, very short time. Oops, I didn't think of that. Hold on. Let me do it this way. So we have hope that this will work. So it's going to be a fraction of a nanosecond, 10 to the minus 11. But the product is going to be of the same order. It's going to be what it's supposed to be, meaning that this, at least in principle, is going to work. Now, a lot more than two questions arise. But let me start with the first question that I think should be addressed. We hopefully understand and know what magnetic confinement means. You have a magnetic field and the particles are forced to follow the magnetic field lines and blah, blah. And therefore, we use the magnetic field to confine the plasma. In the inertial confinement case, there is no magnetic field, or not necessarily. There are hybrid approaches where you use both the magnetic field and the inertial part, but we'll not get into those. Then what is this idea of using inertia to confine the plasma? What does this all come from? Where does this all come from? What does it mean? The idea is that follows. We take a sphere of whatever material we want to use for making our fusion. It doesn't need to be a sphere technically, but we'll get into why that's the only thing that make sense for the type of inertial confinement that we will discuss. Then we make it implode in some way. We'll get to that, of course. And the sphere reduces its size. We start from here, and we make it implode. Sorry about that. That's not what I wanted to do, actually. We go here. And in fact, it's not even, this is not going to be to scale. We'll get into the scales. Now, the way you do it is by having somewhat all the material in your sphere flying inward. And then fusion reactions start happening. The temperature and pressure inside my fuel start increasing, and it tries to expand. So what's keeping it from immediately expanding is the inertia of the fluid or the plasma that's moving inward. That's why it's called inertial confinement. If so that also means if we made this compression happen very, very slowly, there would be very little inertia in the fusion fuel, and my fusion, I want to call it pellet. Well, that's going to be the right word. So let me just call it with its proper name. My fusion pellet would explode in a billion pieces immediately. So will not have any confinement. You may think that, looking at those numbers, 10 to the minus 11 seconds, well, that's pretty much instantaneous. It turns out that it's long enough for a lot of things to happen, and in particular for fusion to happen. You may, if you're an experimentalist, you may also have other thoughts about this approach. One is how on earth are people going to be able to measure anything in something that happens that quickly? Well, I don't know. I'm a theorist, but they do. And that is amazing. And there are things that you can measure relatively easily, like the number of neutrons that are produced in the explosion. There are other things for which amazing diagnostics are used. I cannot speak any more than this on that topic, but it is something to keep in mind. All right, so that is the way we make this happen, by compressing. That's a start, I just noticed. It's supposed to say start, not tart. Sorry about that, that's kind of silly. By compressing large pellet, it turns out this is not going to be large at all. It's going to be, the sizes are 1 millimeter, 1 centimeter, depends on what system you're looking at, but they're already pretty tiny, especially compared to magnetic confinement system. And I compress it a lot of times and get to something very small where the density is so high that I can satisfy Lawson criterion. That is, the energy that gets produced by fusion reactions is sufficient to start an increase in the temperature of my fuel, and that sort of causes not a chain reaction, but what's called the burn wave to propagate through the fuel and burn non-zero amount of the fuel itself. Now, one more thing I want to emphasize about this is the density that is involved. So density is, well, 10 to the 32, again, mean this is in meters. I should, let me make, emphasize that so we don't get confused. Do I have space to do it? I'll make it fit. Perfect, fits. Okay, this is all in SI units, except of course for temperature, but for density, meters to the -3. Now you may wonder how big of a density that is, and the answer to that question, indirect question, is that's pretty high. If you do the math, I'll let you do that. The density is about 1,000 times the density of a liquid. So it's a really, really high density. And that is one of the reasons why the experiments, the tools that are used for ICF can also be used to study matter and in extreme conditions, super high conditions of density and pressure, such as the core of giant planets or other places where we can't easily access the thing we would like to measure. That's called other fields called laboratory astrophysics, where you use the same instruments that you have for ICF and look into extreme matter. And that is the reason why there is a close connection. Today, my spelling is not on my best. Sorry about that. There is a high correlation, close connection between what is called high energy density physics and inertial confinement fusion, because the conditions in ICF are indeed conditions where the energy and the density of the materials involved, particularly plasma, are extremely high. Okay, then the next question is, how do we go from here to there? And the answer is not easily. We've been trying for a while. Well, as I said, we'll get to what NIF did, but we're quite close to where we would like to be. I don't want to call it trick. So let me call it an approach. What is used to do this is what is generally called the rocket effect. Now, you all know how rockets work, at least in general terms. I mean, this is not rocket science. It's a lot harder than rocket science. What you do is I'm going to make a silly drawing here. You have some creature that pretends to be a rocket. Here, perfect. That's clearly a rocket. You can... And then you have gas coming out this way. Oops, sorry about that. And the rocket moves in the opposite direction. That's just Newton's third law. Told you rocket science was easy. So that's what the rocket effect is. Now let's see how that idea has got anything to do with what ICF does. I'm going to take my original big sphere again, make it larger than life, and then I'm going to have something happen to it that makes I used the wrong colors. Sorry about that. Okay, I'm trying. All right, I'm making a disaster. All right, okay, start. I did my arrows in the opposite direction to what I intended, and I'm not supposed to use this color either. Oof. We'll get there. I got this. Okay. That's step one. I'll tell you what that something is in a moment. So something makes the outer layer of my capsule or pellet blow out. Then you see where this is going. It's going to go with me messing up the pen again. The external material flows outward. As usual, I have the color problem that I'll never fix. And therefore, the rest of the capsule great. That's exactly what I wanted to do. Oh boy. All right. Let me try again. I'm going to have an arrow that flies this way. And that's going to start moving inward, which is what we were trying to do. So that's, and this is works exactly in the same way as a rocket. Now you probably already have many questions. We'll try to talk about those in person for sure, but let me give you some ideas of additional things that we may need to think about. Well, first one is, okay, what is that something that's coming in? And that essentially needs to be light. In particular, some, let me call it special type of light. You're going to need lasers or X-rays to make this happen. You need something that brings in a very high intensity, a very high amount of power to make these things at the surface of the capsule blow out. In fact, you may wonder, well, why do I need to use this rocket effect at all? Can I just, just talked about lasers, when I can just shine the laser on my capsule and use the pressure, the pressure of the light to compress it? Well, no, because if you put in enough compression, there is no way that anything else is going to happen other than the outer part of the capsule to explode outwards. And if you use something weaker, you're not going to be able to compress the system. You're sort of in a bind where the only way you can physically make this happen is by the rocket effect. Another thing that you may or may not have thought of yet is the following. If I have a system that looks like this, and I say, okay, I'm going to, believe this crazy idea that we need to use a laser to blow it in. So lasers are blue. Then I'm going to just put a laser in here and make it do whatever it needs to do. Now, if I put a laser in there, there's going to be my rocket effect only happening where the laser is coming, is where the laser is hitting my pellet, and my capsule is going to deform in something like this way. It's just going to deform here, but the rest of the capsule is not going to deform. Okay, first things first, how well am I going to be able to compress the capsule if I do it that way? Well, not very well. I want the whole thing to squeeze in, not just a little piece of it. So that's bad. And also, we're only going to very lightly touch on those, but you're going to put yourself in a condition where instabilities will develop and the whole thing will just break apart without doing any fusion. That's the critical point. So we have two problems with this. Well, then what can we fix it? We can add another laser on the opposite side. And that's going to be more symmetrical. Well, it's going to do two wiggly things in instead of one. It's not very good. And they're even in different colors. That's bad. Okay. Well, then maybe I can use more. Let's say 4. I'll start looking a little better. I'm not going to do any more wiggles, but still not very good. So I go up in numbers. At the end, I'm going to need a lot of them. And ideally, you probably recognize that by now. Ideally, what I want is a completely uniform compression. I want to compress the whole thing, not just some pieces of it. So that will mean conceptually, I need an infinite number of lasers of infinitesimal size to hit the target. That's another keyword that I will keep using. And now you see why it's called a target, because I'm shooting lasers at it. I'm going to want to hit the target with all my lasers, each one of them in the correct point, and do a uniform compression. Well, that's just not going to be possible. And I can't make an infinite number of anything, including but not limited to dollars. Well, anyway, I can't even make one. We have to earn them. All right, and we earn them by learning about plasma physics. What we can do is try to have as symmetrical distribution of lasers on my sphere as possible. And you may wonder what the best number is. Well, it turns out that there are some specific numbers that are going to work better. For instance, 24 is going to work a lot better than 27. It may not be obvious why, but it does, because you wouldn't know where to put the 27, but you do know where to put the 24. That's a geometry problem. And essentially what you do is take the geometry of regular three-dimensional figures, solids, and put one laser in each point of in each corner or vertex of that geometrical shape. And for that reason, the number of lasers always comes in a certain specific quantities, and depending on how what you can do with your specific experiment. You may be able to only have a few, and that may be 12, or even just 4. Then you wouldn't put them this way, of course, because we're completely missing the third dimension. Or you might be able to have 24 or 60 or 192. That's what NIF has, and nobody's trying to do anything bigger. Okay, but that's how that is done. Now, that's not the whole story, as far as that's very far from being the whole story, as far as using lasers to compress the capsule is. There are, in fact, multiple additional things that you need to worry about. One of them is, well, I said this needs to be uniform. Okay, the laser itself is going to be uniform, so I just need to worry about the size of each laser beam that comes in and how to arrange them. Well, that's not quite it. Okay, this is terrible. Let me pause this and be right back. Okay, sorry about that. For some reason, my iPad decided it was time to switch to night mode. It's kind of been dark for an hour. Who understands iPads? I don't. Okay, the laser beams themselves, they need to overlap or just don't overlap in some precise way, so that I am as uniform as possible. And of course, the laser itself is going to be uniform. Well, it turns out the laser itself, it's not perfectly uniform. Far from it, actually. It depends on how you make it. But one big thing that you need to do is work on your lasers so that they're as smooth as possible. And then the intensity of the laser is not going to be also necessarily the same anywhere through the whole beam, but you may not want it to be. Because if that beam overlaps with a neighboring beam, then you don't want the density to be the same, or you have spots where the two beams overlap and they make a double power coming through the same area. And that will be a problem. Here's what I'm saying. If I have one laser beam that looks like this, and another laser beam that looks like they're going to work like this, there's supposed to be both circles and kind of with the same size, then what happens is that I'm going to have too much light going here. So that's if the lasers are identical. They're not going to overlap that much. It's a lousy drawing, but this gives you the concept, the idea. Okay, so that is one thing to be wary of, one of the many. I've only given you very generic expressions. You'll see that I've only written kind of 2 equations today, and I've actually promised you more than one expression for the Lawson criterion, but then ended up only using one. A simplification of that expression comes if you neglect Bremsstrahlung. Maybe I'll bring it in with the next lecture. This is still not the end of the story. This is not the last trick up our physicist's sleeve. So far, we have only discussed what is called direct the direct drive approach to ICF. What do I mean by direct drive is that the light, the laser beam, goes directly into my pellet and produces the rocket effect, which is more technically described as ablation of the external part of the target. Let me put that in writing. Nice. But that's not the only way we can do this. There is another approach, because you'll never guess. Did you? It's called indirect drive. Okay, I can guess from the name that's going to mean that I'm not going to point the lasers directly at the target. I'm going to somewhat point the lasers at something else that are going to do something else to make my laser, my target, implode the way I want. And let's see. Well, a couple of minutes, I'll just start describing it. So I don't want to leave you hanging, even though that's, I hear, a good strategy for keeping people interested. What you're going to do is the following. You're going to have your target. I'm going to draw it a little smaller now. You're going to put it in some type of container. This is going to be cylindrical, where that's going to be my axis of symmetry. So imagine, maybe I can try to do a little better here, drawing it this way. So that's kind of what it's supposed to look like. I hope you get the idea. If not, I'm going to tell you what this thing is called, and you go on Google and you find it. And I'm actually going to shine my lasers coming from the outside of the system. I'm going to shine them here. And then with the only color I have not used, I'm going to have something else coming out of here, and that's going to be X-rays. All right, time to close. Let me just give you a couple of names, or one name, which is all round. I don't know why it's a German word. I mean, I know why it's a German word. It comes from German, but I don't know why a German word is used. And I'm going to have X-rays that are going to compress my target. Okay, we'll talk a little bit more about this in the next lecture. Thank you for listening in, and I will see you for lecture 15.